what I would say is Karl is one of the leading neuroscientists, and he's one of the great exponents of the successes of the current AI frameworks. But on top of which, going back to the unreasonable effectiveness of mathematics, I think that the line of mathematics that he wants to sort of propound and show as being very effective is the free energy principle, that at the heart of the matter, there is some element, he calls them surprisals, that you would want to minimize. And general intelligence, going back to our previous meeting at the webinar on AI and general intelligence on the November 5th, I completely agree with him that the basis of general intelligence would be to minimize, to keep life's vitals, as it were, in a narrow range, and you wouldn't want any surprisals there. So to sort of think that the free energy principle would give us a unified framework for intelligence itself is Karl's way of addressing the unreasonable effectiveness of mathematics. So Karl, on to you.
Thank you very much. It's a great pleasure to be here, and a privilege to talk to such a wide range of expertise and investments. I am effectively going to tell exactly the same story that Hector told, but using a slightly different language. So forgive me for any repetition. So my talk's going to be about how to address general intelligence from the point of view of sentient behavior. And I use sentient behavior deliberately because there's sentience and sense making under the hood, but it's also inactive in the sense that it is about behavior and making choices, and actively, as we will see, sampling those data that you're making sense of. So I'm going to frame that in terms of what philosophers call self-evidencing, and motivate it from the point of view of normative models of sentient behavior, or generalized intelligence, with a particular focus on what this kind of perspective gives you in relation to AI research. And then I'll rush through some practical aspects using simulations just to unpack the basic ideas, but they're going to be very trivial simulations in relation to what we have been hearing about during the previous talks. It's just going to be trying to understand how a little animal chooses to look over there or look over here. So the notion of self-evidencing rests upon a very simple assumption that is underwritten by, we'll see at the end, a physics of sentience that comes from trying to understand self-organization from the point of view of non-equilibrium steady state physics. But for the moment, I'm just going to assume that all of action and perception can be summarized in terms of optimizing beliefs. And by beliefs, I mean conditional probability distributions that are physically represented or encoded or parameterized by some state of an artifact, a sentient artifact. And I'm denoting those beliefs about the things that the artifact or the agent doesn't know, basically states of affairs in the world, causing its observable observations, and what it's actually doing in terms of control variables or policies. And the argument is that a sufficient explanation for all behavior that may be imperative from an existential point of view is that you just want to maximize the marginal likelihood of your observables, the things that you measure, under a causal cause-effect model, a generative model, a statistical model that could be cast in terms of symbols, or it could be cast in terms of continuous variables, a model of how those consequences, the observable consequences, were caused. I'm going to motivate this simple specification of normative behavior, optimal behavior, in terms of this optimization, just by looking at what other general formulations of sentient behavior would look like from the lens of this formulation. So if I take the log of this marginal likelihood, also known, as we'll see in a second, as model evidence in Bayesian statistics, then I've got a nice proxy for value, in the sense that everything I choose to do, or the beliefs about what I am going to do, will be in the service of maximizing this value, if I afford value to these observations here. And what we'll see in a moment is that we can estimate or evaluate a lower bound on this log marginal likelihood, that if you treat it as value, leads to formulations in terms of reinforcement learning, optimal control theory in engineering, and economics expected utility theory. If you were an information theorist, you would take the negative of this and treat it as a self-information or surprisal, or more simply surprise, that underwrites formulations of good behavior in terms of things like the principle of maximum mutual information, Horace Barlow's minimum redundancy or maximum efficiency principle, and indeed the free energy principle that inherits from this evidence lower bound here. That's nice, because the average of self-information is entropy, which means that this will look as if it's trying to minimize entropy, or the dispersion of its observable exchanges with the outside world, or its eco-niche. And of course, that is the holy grail of things like self-organization in synergetics. And indeed, if I was a physiologist, it's just a statement of homeostasis, that my beliefs about the states of the world and my beliefs about what I'm doing are in the service of keeping my observable interactions with the world, my physiology, within viable bounds, and stopping their dispersion and the tendency to disorder. If I were a statistician, then I would simply call this marginal likelihood model evidence. The evidence inherent in these outcomes, these data, that under a given model, where I simply am the model of how those outcomes were generated. So that's my motivation. That free energy inherits from two sources, and I say this in relation to the previous discussion with Hector and Sherry. You can either trace it from the work of Richard Feynman and the path integral formulation as a device to make an impossible marginalization or integration problem tractable by converting it into an optimization problem by creating or constructing a bound on something you want to optimize. Or you can see its heritage or its lineage as deriving from Kolmogorov complexity minimum description length and minimum message length. So depending upon your favorite kind of maths, you get to this same quantity. So what is this quantity? It's essentially a quantity that articulates James's maximum entropy principle, but making the point very clearly that the entropy that we are talking about is the entropy of our beliefs about states of the world generating our observable outcomes under constraints. And the constraints in this instance are supplied by a negative energy and are supplied, usually decomposed into a log likelihood and a log prior. And that's key in the sense that these two things together provide a probabilistic description of the cause-effect relationships, or the joint distribution of causes and consequences. And that, in my world, is referred to as a generative model. Exactly the same kind of concept underlies generative adversarial networks and the like. So everything I'm going to say really rests upon committing to a generative model, and then everything else is about optimizing that model and making inferences under that model. Just to illustrate what this brings to the table in a very sort of broad brush sense, what I've done here is just rearranged that expression and divided it into something that a statistician would recognize immediately. First of all, making the point that I can rearrange this into an accuracy, the expected log likelihood of some observations expected under my beliefs about those observations. And then we have this term, which is a complexity term, which is a KL divergence, that basically equips the free energy with a role as a bound upon the thing that I want to optimize, the marginal likelihood here. This complexity is really interesting because, from my perspective, this has cropped up on a number of occasions throughout certainly the last session or two. Technically, it's just the KL divergence between my beliefs, having observed some data, and my prior beliefs. So it's the degree to which I have changed my mind. If I was a computer scientist or a statistician, it's the statement or the quantification of my belief updating in terms of bits or nats, as scored by the relative entropy between my posterior beliefs after seeing the data and my prior beliefs, the degrees of freedom I am using up in order to provide an accurate explanation of what's going on. Slightly contrary to Hector, who saw statistics as being subsumed under algorithms, my perspective, which I'm willing to change, is I would see it the other way around. That in the limiting case that your states are quantum states, and in the limiting case of large numbers, this now becomes Kolmogorov-like complexity, and from that you can develop some of induction and universal computation, all in the service of finding the simplest explanation for some observations. And what we're basically going to see, the second key point, other than the first key point, which is at the root of all this, is a generative model that entails a cause-effect relationship. The second point is, if you want to make this calculus speak to choices and action and decisions, then you have to think about what this kind of self-evidencing means for the consequences of a choice or a decision or an act. So what we're going to see basically is that we're going to choose those behaviors that maximize the accuracy expected following a particular move or choice, and complexity. And what we'll see is that this translates into optimum Bayesian design principles. So this, we've heard about this in terms of little sensors in classrooms, I think during Rosella's talk, finding the right data, designing the right kinds of experiments to solicit the data that's going to be maximally informative in reducing your uncertainty about the causes of your observations. This complexity term, when you think about its expectation under the posterior predictive density in the future, we're going to see underwrites Bayes optimality in a Bayesian decision theoretic sense. And the two together, literally added together, are going to, in this talk, be cast as self-evidencing, namely acting to maximize your expected free energy. And the way that I normally motivate that is to ask the audience, imagine you're an owl and you're hungry. So what are you going to do? Let me ask somebody. Sherry, what are you going to do? You're very hungry. She's got her microphone off, but it doesn't matter.
Right. No, I'll obviously look for some prey, but But how is that figured in your statistical model?
Well, we're going to find out now, because that was a perfect answer, looking for some prey. So in looking for some prey, and let's just see the owl looking for its prey, there is that answer, I think, reveals some deep truths about a question that you might pose yourself. If you had to commit to some maths or some principle in order to identify the best thing to do next, you can go one of two ways. So I'm deliberately introducing this dialectic. I'm going to repair it later. One's going to become a special case of the other. But I think this dialectic is really useful and is informed by Sherry's answer. We can either assume the existence of some value function, of some states that would ensue if I took this action U sub t And then if I could evaluate that value function, I could identify the thing that I should do whenever I was in this particular state to generate the next most valuable state. And that view, as we'll see in a second, predicated on Bellman's optimality principle, assumes that optimal action depends upon states of the world. The problem with that, though, is inherent in Sherry's answer. So if I cast I'm going to look for food as resolving uncertainty about the location of my prey, then immediately that tells me that the uncertainty, the thing that I'm optimizing, is an attribute of a belief. So uncertainty is an attribute of belief. Therefore, what I'm actually optimizing is not a state of the world. I'm optimizing, optimal action depends upon beliefs about states of the world. So your action depends upon your current beliefs. And this is about where was your prey. So I'm denoting that with a very different kind of construction where we're talking about a functional of beliefs about what will happen if I did that. Furthermore, it matters the order in which I do things. So it matters whether I look for my food, then I eat it, or I try to eat it and then I look for my food. And that tells you immediately that the optimal action has to be sensitive to the sequence of actions in the world. And I've written that down here as a sum of this functional here, which is going to be an energy functional. So this becomes an action or a path integral or time integral of an energy. So this gives you a very different perspective on what the best things are to do, in the sense that now we're going to be context sensitive to the beliefs about our current beliefs about the world, and we're going to be minimizing this path integral or optimizing this path integral of an energy function. And I phrase it like that because you've got these very two distinct ways of writing down a first principle account of normative behavior, optimal behavior. You've got this Bellman optimality-like approach that would be applicable in the domain of optimal control theory, deep reinforcement learning, Bayesian decision theory, and so on. Contrasted with this belief-based scheme that looks much more and just is a variational principle of stationary action, including things like the free energy principle or in a biological context, active inference, also subsuming things like artificial curiosity and intrinsic motivation, optimal Bayesian design, information seeking of an optimal sort in the context of face of uncertainty in things like partially observed Markov decision processes. So what I want to do now is, and Sherry, you must tell me when I'm 5 minutes before the end. I'm not going to get to the end of this presentation. I don't think it matters because I imagine there's going to be more interesting discussions than me doing a show and tell. But this is...
You've got about 5 minutes before we get to some questions.
Okay. So this is just a rehearsal of the what I've just said in reference to the functional form of this variational free energy. For those people in machine learning, this is just the evidence lower bound. So I've written out the free energy here, and that action or the expected free energy that is a functional of my beliefs consequent upon a particular sequence of actions or some policy here. And I've done that just to show the beautiful symmetry between the functional forms for the free energy, which is the evidence lower bound, and the expected free energy. So here again, we have our free energy written in terms of complexity and accuracy. I can switch, just move the terms around to carve it up interpretationally in a different way, just to reiterate, it is a bound on log evidence, and it's exactly the same bound you use in a variational autoencoder. This is exactly the same quantity. If we now take this quantity and take its expectation under the outcomes that a posteriori I predict I would encounter should I make that choice or commit to that policy, then we end up with a formally similar expression, but now conditioned upon the policy. So I just want to go through what that expression means or how it could be interpreted from different perspectives. First of all, let's just forget about this sort of log of the marginal likelihood here and just focus on the expected bound here, or KL divergence here. So what is this? Well, it's another KL divergence. It's a KL divergence that scores the difference between my beliefs after seeing these fictive outcomes in the future, given my policy, relative to what I believe in the absence of those observations. So it scores the information gain. It scores the, in the visual search literature, this is known as Bayesian surprise. It scores the resolution of uncertainty. And of course, it is just basically an expected, or it is a mutual information. If I now remove a particular source of uncertainty from the world, let's remove ambiguity. So how might I do that? Well, let's imagine that I had sufficient number of sensors or data points, and they were virtually noiseless. So there's no real difference between my observations and the things that were causing my observations. So there's no ambiguity about the world. There's no uncertainty about observations given states of the world. These two can now be merged. And I'm just left with this, which is the expected complexity cost that we were talking about before, the thing that underwrites efficient explanations, the simplest explanations. So what's this KL divergence? Well, it's simply the difference between my anticipated states, outcomes in the future, or observations in the future, if I pursued this policy, relative to my prior preferences, the kind of outcomes or the underlying causes that a priori I expect to encounter. And in engineering, this is just KL control. And economics, it could be read as risk-sensitive control. It just scores the divergence of outcomes from one's prior preferences. And if I make the final move to remove the kind of uncertainty inherent in the reducible uncertainty that I could resolve by active sensing, by active learning, sampling the right kind of data that resolves all the uncertainty that is reducible or resolvable, I'm just left with this. And what is this? Well, we started with this in the first slide. It's just the expected value. So what we are talking about then is a calculus that suggests that you will always appear to or choose policies that either minimize risk or minimize a mixture of risk and ambiguity, or they will maximize the intrinsic and extrinsic value. This is sometimes known as intrinsic motivation, and the extrinsic value would just be the expected value from an economic or utilitarian perspective. So this just summarizes what we've been talking about here, framed from the point of view of a Bayesian statistician, that in optimizing expected free energy with respect to a policy, we are implicitly choosing those policies that result in the greatest expected value. That is, of course, the objective function behind Bayesian decision theory, when your value now plays the role of a negative cost function or loss function. At the same time, you're going to be maximizing the information gain. So we've got Bayes optimal decisions with optimal design basically equals active inference. And then if I had time, now I know I don't, so I'm going to...
Karl, can I ask you, remember you say that in one of your drafts, which you then edited out, you said searching under the lamppost is not what you would be recommending, because, you know, there are some economists here and some of them would see this as naked optimization within given the set, a choice set, since you can't do anything new. But I know you say that you can do more out of this framework. There's an additional term, which I don't see, or you haven't emphasized that, for which you would be searching novel outcomes.
Yeah, it's a great point, which I suspect we'll come back to in the general discussion. But yeah, you're absolutely right. I've just been talking about sort of inference about states, that are time dependent. This whole story is hierarchically embedded, so that then you have uncertainty about the parameters of a generative model. You then have uncertainty about the structure of a generative model. The same maths applies. So the intrinsic value, that which underwrites curious behavior, also applies to your posteriors over the parameters of your generative model. If you're in machine learning, these would be your posteriors over the weights, for example. They're never actually articulated in most deep learning I know about, but if you had a fully comprehensive deep learning machine where you also had posteriors about weights, then you would make moves that disclose or resolve uncertainty about the contingencies and the associations that are parameterized by the weight matrix. That would look like novelty-seeking behavior. And then you take it to the next level, which is the very structure of the model itself. And then you would make moves that try to find the right structure. And at that point, we come to what you were talking about with Hector, which is, where do you explore in that imperative to search for novel structures and novel explanations? And now you are in a truly categorical symbolic world, because we're talking about structures of models. Does it have an extra factor? Is there an extra layer? Does this relationship exist or not? And that's a really deep but really important problem, which one could argue has been solved by natural selection in the sense of Bayesian model selection. So that would be the one way of casting structural learning, if you were, say, from radical constructivism. You've distracted me, so I can't even fast forward through the rest. But what I would have done is just take you through the mechanics of this. It's nice because it is actually exactly the same belief propagation, I think, that Tim Rogers was talking about. I can't quite remember, but certainly it has come up. You can just take off-the-shelf stuff that does this belief propagation, given a generative model. And crucially and interestingly, in relation to Hector's talk, almost universally nowadays, when we apply this to real-world scenarios, we use discrete state space machines and discrete state space generative models that have an easy reading in terms of symbolic manipulations. If this, then that. And you can write it down very much in terms of things like modal logic, just simply because you're dealing with, in this instance, Markov decision processes or partially observed MDPs. And I would have taken you through Forney style or normal style factor graphs and the nature of belief propagation and how that looks very much like the brain. And then I've given you a very simple example of a little mouse searching for food, given instructional cues that tells it where its food is, and showed a deterministic but Bayes optimal progression from exploitative exploration, active sensing, uncertainty reducing behavior through to exploitative preference seeking, goal seeking behavior. And I would have then shown you.
Karl, I'll have to stop you here.
Right. Showed you some of that, and then
yes, because I think we need to get some questions from our audience. Shyam, I mean, since Shyam's well known for zero intelligence agents, he's somewhat violently against this maximalist optimization. I've got him here from Yale. So yeah, do you want to open the questions to Karl?
I'm not sure if it's a question for Karl or for Hector. Maybe both. So I imagine a world which will be dominated by these artificial agents, by AI agents, driven agents. What do we know about how well these artificial agent theories will work in that world where data itself is being generated by a population of agents which are dominated by such agents?
So That sounds like something that Vincent might come to. It's about self-reflexivity, is it? That agents produce information that, of course, it can be manipulative always, sometimes. And Hector, do you want to answer that?
I think Karl wanted to say something.
You're passing the buck, Karl, then.
I want to hear what Hector has to say before I say so.
So let me understand the question. So the question is if agents themselves are generating the data and then they are also making the inference calls. Is that the question?
We are living in a world now where the role of AI is on the increase.
Mm-hmm.
Is that fair? Okay. Now, let's imagine a world where it is artificial intelligence which dominates the world. So the data being generated is being gathered from a world where agents themselves are artificial agents, not human agents. We learned many models and theories in these two talks about the properties of AI systems. I'm trying to understand how well will the AI systems work where data itself is being generated mostly, not entirely, but mostly by AI agents.
Yeah, I see. There are so many angles, but one I can perhaps explore a little bit is that at some point, and that's what we have to be careful about, I think there could be a disconnection of how we perform science from actually how they perform science, because then things like, for example, asking them to communicate with humans would no longer be necessary, right? And in some cases, we may or may not need humans to understand what is going on. So in some way, I think there's an opportunity for AI to accelerate science, but we are going to lose also understanding of how that science was performed, and that's what we are going to lose eventually, perhaps. But it is humans who have to decide whether that science should continue be performed in such a way, or should be taken back to actually be just interpretable by human scientists.
Let me, Hector, if I may pursue this a little bit more. Will it be the case that any AI system will become self-fulfilling in this world?
Shyam, if I may, actually, Vincent's talk will be on these issues of singularity.
Sure. Okay, let's postpone
Vincent's on a train, so can we put it off till then?
Of course. Thank you.
I saw another hand, and India's hand was up. Do you want to ask a question?
Yeah, so there's a question to Karl. This framework is very fascinating. I have basically one very specific query. So in epistemological game theory, it's actually quite common to, pursue this Bayesian approach to say that it's not so much about the fact that there are, given probabilities which people are already aware of. So given the particular example that you gave about an owl and a rat, how does, so you had set it up, if I may use the word, in a decision theoretic framework. I was just wondering how would it translate into a strategic framework, like a game theoretic framework, where, this is a standard example that there is a predator and a prey, and the prey will, whatever the prey does, will also change my state space. So does it just directly translate into incorporating strategic behavior, or is there some more modifications that are required on the inequalities that you are showing us?
That's a great question, and in a sense, it actually speaks to the previous question. So what you're asking now is, you've got two sentient systems, or possibly an ensemble or a population of systems that are all trying to actively infer each other. And this is not something that is so developed in the literature, but it really is a tremendously important focus when you put two of these self-evidencing systems, so that now their actions become the observations for the other, and vice versa. There's now a dyadic or generalized coupling amongst a whole bunch of these things. What tends to happen is, because that variational free energy is an extensive quantity, the free energy solution of the ensemble or the population or the dyad is that which is the sum of the variational free energies of each of the elements. And just heuristically, what tends to happen is, if you read that free energy in the spirit that Sherry was talking about, which is basically predictability. So if I can predict what's going on, I have an accurate model, and it is a simple model, and therefore it will generalize and it will elude sharp minima. Then that means I aspire to make the world very predictable. And the simplest way for an ensemble or two agents to make the world as predictable as possible, when the world is constituted by the other agent, is for them to do the same thing. So you get something called a generalized synchronization. So everything sort of converges towards the same generative model, or more poetically, a shared narrative about how to exchange. So everything starts to sing from the same hymn sheet.
So Karl, let me jump in there. Remember, Ken Binmore is not with us. This is exactly the problem that he says it has created a problem in game theory. In game theory, you don't have this agent, which I will call Gödel's liar, the adversarial agent. So in the natural sort of predator-prey things, they do just look at it as nonlinearity. But in the actual algorithmic game, in which, or digital game, which is involved, the virus and the host and that sort of thing, certainty is going to be punished. So that's where your free energy principle, in some sense, gets unstuck, because you can't minimize. It's not in your gift to minimize surprisals. You'll be forced into radical novelty-producing outcomes, and that'll only sort of accelerate. So you are forced into more and more complex system, or in what I would call Gödel incompleteness. So on one hand, this is the point that your Matteo Colombo was criticizing you about. On one hand, I agree that we would like to remove surprisals with regard to all of life's vitals, that is homeostasis, or whatever, some people call it allostatus. But in order to achieve that in multicellular life, we are propelled into open-ended search for novelty, because there is a virus or an opposition or adversarial agent in that system.
Yes, well, that would be an emergent property of an ensemble where you had initially symmetry breaking. So any heterogeneity will be manifest. And you're absolutely right that in virtue of trying to optimize your expected free energy, you will become novelty hungry. But novelty about what? What will you be exploring? Will you be exploring an increasingly complex world that is actually generated by other things like you that are becoming increasingly complex? So that, again, it speaks to the very first question.
Yeah, like you said, two opposing sentient agents, or two such opposing, I call them digital agents, capable of novelty production. The world, so this is where, on one hand, we know that these are arms races, these are Red Queen sort of races. And on one hand, everything remains the same, but on the other, you are propelled into complex behaviors and unforeseen novelty, So this is the problem. I think the free energy principle is fine, except it can't, unless you fess up to this problem, which actually you do say that. I think I quote you say that, a lot of people think that free energy is all about being in the dark room, right? You don't need to do very much. You keep saying you just turn on the light, but I'm going to argue turning on the light is a non-trivial exercise, right? Turning on the light to do something, novelty searching and so on and so forth. It is not a given. It's something very unique to life itself, right?
Yes, well, switching on the light is a nice example of making a move or committing to a policy that minimizes the ambiguity, for example. So, again, light switching on is something that is prescribed and is characteristic of an expected free energy optimizing agent. There is some interesting work by Jean Denisot, who put a whole bunch of different free energy minimizing agents together and was played out economics games, looking specifically at the degree of sophistication. So in the generative model, I have a model of you, and in my model of you, you have a model of me. And the question is, to what level of sophistication do I embed my generative models? And he actually, using numerical analyses, showed that there was an ESS, an evolutionary stable strategy, where half the people were really, really unsophisticated and the other half were very, very sophisticated. So if you break the symmetry at the beginning, you can get, this wasn't quite Red Queen dynamics, but it was certainly an interesting dissociation where some people actually dumbed down, but other people became much, much more complex. And that was a steady state solution born of and only of maximizing, because we're in a machine learning context, maximizing their free energy. So all of these features should be emergent properties.
Yeah, so this is where maybe logic comes in, right? I begin to see that there is no function that you're actually capable of maximizing or minimizing. I challenge that there is such a function. There is only one principle that I would argue. It's not one of necessarily free energy, but of consistency. If you go into logic of how these things are going to be organized within, individual beings.